give you some notes that you can get started with in order to complete that homework. All right, so the first two problems on the homework you should be able to do now if you've looked at it. I just posted the homework a couple hours ago, so you probably haven't seen it. Then the third problem, you actually have to design a what they call a compound gear, gear train to do it. So let's talk about gear trains. So what I'll do is I'll post these notes on Blackboard since I know people aren't here and are leaving now. So I will post these after class so that those people have access to them. So let me go ahead and draw the gear train. So you may want to see page 504, figure 928. All right. So what we do is we label these things. Ground is always 1. So start with the pinion gear. This is the pinion. And then you have gear 3, 4, 5, and 6 in this case. And then you may have your omega n set to plus omega 2. So that means that this is rotating this way. This is your omega 2. If omega 2 is rotating like that, omega 3 is going like this. Omega 4 is going like this. Omega 5, the opposite direction. And omega 6 going like this. All right, and that is equal to your omega out. Okay. So you have a plus omega 6 output, and you have a plus omega 2 as your input. So if you go ahead and look at the output omega over the input omega, let me just do these individually. If I label the pitch points, P, Q, R, and T. At P, I have omega 3, that's the output, over omega 2, which equals minus n2 over n3. The minus sign is coming into play there because we got a positive input and we got a negative output. So we got to capture that with a minus sign there. And it's omega 2, n2 cross, look at it cross this way, omega 3, n3. This is gear tooth counts. The gear tooth count corresponds to the radius of the gear. It has to have the radius of the gears have to have the same ratio as the gear tooth counts on the respective gears. We covered that last time. So at Q, I have omega 4 over omega 3 equals minus n3 over n4. At R, I have omega 5 over omega 6, which equals minus n6 over n5. And then lastly, at T, I have omega 6. Oh, I'm sorry. 4, 3, 4, 5. This is 4. Sorry about that. Omega 6 over omega 5 equals minus n5 over n6. All right. So if I go ahead and kind of concatenate these, multiply them out, your omega out over your omega ins, I have a omega 2, omega 3, here's omega 3 over omega 2, times omega 4 over omega 3, which is this one, times this one here, omega 5 over omega 4, times the last one, omega 6 over omega 5. And when I do that, watch what happens. These cancel out, these cancel out, these cancel out. And so I'm left with this equaling my omega 6 over my omega 2. Okay? Everybody see what's going on there?
So the negative n over n is always negative unless it's internal meshing, right?
Right. So let me put this thing here is equal to, and I can make the direct substitutions, n2 over n3 minus n3 over n4 minus n4 over n5 minus n5 over n6. And watch what happens here. So this simply equals n minus n2. Let's see, that's a positive. I think we're left with, we're left with a negative. All right. It should be positive, shouldn't it?
That's the first one. Because they rotate in the same direction.
Oh yeah, there. Thank you. Thank you, math, for doing that for me. So math does work out. All right? Because you have positive omega 2 and you have positive omega 6. So it does work out. All right? So the takeaway here, let me just write it down. Notice N3, N4, N5 sizes have no influence on overall gear train value other than influencing direction. Okay? In other words, gear 3, 4, and 5 could be any size we want. I mean, they could be huge or like little ones. And they have no impact on the gear train value. All right? The only two gears that matter in this case are 2 and 6. And so by looking at that scale, it looks like 6 is about 1.5 times the size of 2. So the gear train value is a 1.5 to 1 gear train value. Okay? N3, N4, N5 are known as idler gears. Idler gears only influence direction. Okay. All right. So, there's a rule that we're going to follow here. No two meeting pairs of gears should exceed a 10-to-1 ratio. So no ratios between two meeting pairs of gears can be higher than 10-to-1, more than 10-to-1. All right? And there's a reason for that. And that reason is large forces on pinion teeth lead to tooth failure. So what I'm trying to say here is that if you have something like this here, where you have just a little small pinion, and you have a huge gear that's mating. All right. So what happens here is that there's so much torque available on this thing here that the interface between this little pinion gear and this big one, and this here is more than 10-to-1. You can see that it probably looks to be 12 or 13-to-1, the size ratio. The tooth interface on here, because the forces are so large, they'll break the tooth on the pinion. And if you break a tooth on a gear, the other teeth are just going to come, follow along. They'll break also. Okay? So that's why we maintain something less than 10-to-1. Wait.
I thought you said at Capstone that they did something similar to that. Do they use a different method?
They do. In fact, we have to use compound gears in order to get ratios greater than 10-to-1. All right? So that's what we're going to show, and that's the third homework problem that's due on a week from Wednesday, is a compound gear. So, you know, let's write down that question. Then, how do we obtain gear train values greater than 10 to 1, like on capstone, right? The answer is compound gears. Gear train system. And what a compound gear train means that more than one gear is carried on each shaft. Note, still adhere to individual gear meshings less than or equal to 10 to 1. Right? So this is in section 9.8, compound gears. Figure 929, page 505. So let me show you what this looks like.
Is it 504 or 509?
504, I have it. 504, sorry. Yeah, 504. So my mouth is wrong, my writing is right. Okay. So if I look at something like this, so let me draw a compound gear set.
Can you zoom out?